Hi, in this video we'll talk about spatial image resolution and contrast. When you think of resolution, then the first thing that comes to your mind is probably the number of pixels on your sensor. For example, this camera has a 24 megapixel sensor with a width of 6000 pixels and a height of 4000 pixels. But spatial resolution is much more than just the width and height of the sensor. It's affected by factors like the size of the pixels, the aperture, the wavelength of the light that you're capturing, and of the quality of your lens. And in this video, we'll talk about how these factors affect image resolution, and on the way, we'll cover a few topics like diffraction and MTF charts. So let's get started. Spatial resolution refers to the finest details we can capture in our images. So let's start with our lens, because that's the first place where light reaches our optical system. For the moment, let's assume that we're using a perfect lens, a lens that doesn't suffer from any kind of aberrations. So there's no distortion, no spherical aberrations, no chromatic aberration, no coma or anything else. The lens is perfect, so its shape and material doesn't reduce the quality of our image. However, the aperture does affect the image quality. And that's because light that goes through an aperture suffers from diffraction. Let's have a closer look at it. I'm going to show you a visualization to give you more intuition of what's happening. Let's assume that we take an image of a single, very bright point far away. That point is tiny, infinitesimally small. As the light from that point goes through an aperture and hits some surface, the result is not a tiny, infinitesimally small point, but a pattern like this one. This is a two-dimensional visualization, and if we just take a slice through the center of the pattern, then it looks like this. That's an empirical observation. If you do an experiment, then you can see this pattern. And the exact pattern that you get depends on the diameter of the aperture, on the focal length, and on the wavelength of the light. The pattern is called the Airy pattern, and the area around the peak in the center is called the Airy disk. So this behavior is something that we can observe, and why it happens has to do with the nature of light. The best models that we have to explain it are based on quantum mechanics, and I think they're too complicated for this video. So instead, I'll show you a model from classical physics that's intuitive and that explains the results well, but that is not the best, most low-level model that we have. The model is called the Huygens-Fresnel principle. In this model, we assume that light is a classical wave, similar to this one, and the model assumes that each point on the wave gives rise to a new wave. So for example, let's look at a simplified version of the aperture in our camera. This is the point in the center of the aperture, and it gives rise to a wave like this one. This is another point on the aperture, and it gives rise to a wave like this one. And those two waves interact with each other. In some places they reinforce each other, and in other places they cancel each other out. And that happens not just for the 2 points that I've shown here, but for all infinitely many points on the aperture. And the result of the interference among all those individual waves is the Airy pattern that we saw before. Okay, so how does this Airy pattern affect the resolution of our image? Let's assume that we take a picture of 2 points. Here, the points are far away from each other, so we can easily tell them apart. But as they come closer to each other, their signals start to overlap, and it becomes more difficult to resolve them. And at some point, it becomes impossible to tell them apart. So there is an absolute, physics-imposed limit on the resolution that we can achieve. That's called the diffraction limit. It's impossible to tell 2 points apart whose distance is at or below the diffraction limit, regardless of how well manufactured our lens and sensor are, and regardless of how perfect the lighting conditions are when we take the photos. If the distances between the points is a bit larger, like for example here, then we can tell them apart. But the difference between the peaks and the dip between them is very small. There's very little contrast. In this case, the dip in the middle is just 3.4% below the 2 peaks. So even though theoretically we could tell the 2 points apart, practically, when considering that there is, for example, noise in the image, or if there are slightly varying lighting conditions across the image, we probably still can't tell those 2 peaks apart. There's too little contrast. I've mentioned the word contrast twice now. So what exactly is contrast? There are different definitions. For now, while we're talking about Airy patterns, we just use the relative height of the peaks and of the dip between the peaks. So if this gap here is large, then there's a lot of contrast because the two peaks are clearly separated by a dark area in between them. If it's small, then there is very little contrast because the gap has almost the same intensity as the two peaks. Later on, we'll also talk about a different way of computing contrast. So, if, in practice, we can't resolve 2 points with 3.4% contrast, how much contrast do we need to be able to resolve them? The exact value will depend on a lot of things like the noise in your hardware and the lighting conditions. But a common criterion that's often used to describe the achievable diffraction limited resolution is called the Rayleigh criterion. It's a bit arbitrary, but it's easy to compute. According to that criterion, 2 points can be resolved if the center of one Airy pattern is at the first minimum of the other Airy pattern. So our resolution under this criterion is limited by the radius of the Airy disk, which is 2.5 micrometers in this example. And with this criterion, the dip between the two maxima is about 26.5%. So diffraction clearly has an impact on the resolution that we can achieve. But it's a little complicated to evaluate exactly how it affects our system, because that depends on the minimum contrast that we need for our application. Okay, so far we've talked about the distance between 2 points in micrometers. But when talking about resolution, it's common to use spatial frequencies instead. And spatial frequencies are usually expressed in line pairs per millimeter, or cycles per millimeter. What is that? I'll explain in a moment, but rather than looking at points like we did before, we'll now use different patterns. For example, this is a line pattern which contains black and white lines. The white lines represent a lot of light, similar to a peak in the Airy pattern, and the black lines represent little light, similar to a trough in the Airy pattern. To be able to tell two white lines apart, we always need a black line between them. Without a black line, it would just look as if there was one large white line. So it's convenient to group a black line and a white line together, so we get a pair of lines or line pair. Instead of the line pattern, let's now look at a wave pattern. Waves are very useful, and later in this video we'll look at why that's the case. In a wave, this distance here, which contains one peak and one trough, is called a cycle. And when talking about resolution, line pairs and cycles are used interchangeably. Let's look at the line pattern again. If we know the width of a line, then we know that a pair of lines, or a cycle, has twice that width. And we also know how many of these cycles fit into a millimeter. So we can compute the number of cycles per millimeter. And this is called a spatial frequency because the unit is per millimeter, similar to how in audio the frequency unit hertz refers to per second. For example, earlier we talked about the Rayleigh criterion, and we found that the radius of the Airy disk is 2.5 micrometers in this example. This radius already contains a peak and a trough, so it represents the width of a cycle. And the corresponding spatial frequency is 390 cycles per millimeter, or 390 line pairs per millimeter. Okay, now we're moving away from the Airy pattern, which is very close to the actual observations, and instead we'll focus mostly on these wave patterns, which are more of a mathematical tool. I said before that wave patterns are very useful, and that's because any pattern can be written as a sum of sinusoidal, so wave patterns with different frequencies. Even a pattern with jumps, like the line pattern that we saw before, can be written as a sum of waves. So if we know how these waves are affected by diffraction, then we can find the effect of diffraction on any kind of pattern. Let's look at the line pattern as an example. This is the pattern that we get if we just use two waves with two very low frequencies. But as we add more waves with higher frequencies, the pattern starts to look more and more like the line pattern. Using waves like this is a mathematical tool called the Fourier Series. and it's widely used in signal processing because it's a very powerful tool. This plot here shows how much of each frequency we need to create a line pattern. So the horizontal axis refers to the frequency of a sinusoidal wave, and the vertical axis tells us roughly how much of that frequency we need to reconstruct the signal. So how does this relate to diffraction? Let's look at a wave pattern. As the light from this pattern goes through our aperture, it's affected by diffraction. So the light from each point of that wave pattern creates its own Airy pattern. By the way, these are simplified examples. The actual wavelets are computed in 2 dimensions, and I've also scaled them up so they're easier to see. Okay, so the light from all of those 2D wavelets from all points is then combined, and the image that we get on the other side of the aperture is made up of the sum of the Airy patterns of all points on the wave. The pattern that we get out is still a wave, but it's not as tall as before. Its amplitude has decreased. So the difference between the brighter spots and the darker spots has decreased, which means that the signal that comes out of the aperture has a lower contrast than the signal that went in. The contrast for a wave like this is best described by the Michelson contrast and is defined like this. Our wave here, which has a spatial frequency of 200 cycles per millimeter, has a contrast of 50%. So let's plot this on its own graph. And we can do this for waves with different frequencies. And if we do this for waves with many different frequencies, then we get a line like this one. The black line that you see here is actually computed from an analytical solution. The red dots are based on simulations. They don't match exactly, because in simulations there are usually some numerical errors and some discretization errors. But anyway, you can see that the contrast goes to 0 as the frequency reaches about 472 cycles per millimeter. This cutoff frequency can also be calculated with this formula here. A chart like this is called a modulation transfer chart, or an MTF chart, and it shows how contrast gets transferred from the scene onto our image. This chart here only contains one line for the diffraction limit, so it shows what we'd get if we had a perfect lens. But when you look at the datasheet of a real lens, then there are usually many lines, and they're usually below the line for the diffraction limit. And that's because real lenses suffer from errors, and those errors affect the resolution and contrast that we can achieve. A high quality lens will have lines that are closer to the diffraction limit. A lower quality lens will have lines that are much lower than the diffraction limit. So why are there multiple lines? That's because the errors that affect lenses are not the same across the entire image. On this MTF chart, the blue lines refer to the contrast in the center of the image. The green lines refer to a point that's about 6 millimeters away from the center, and the red lines to about 9 millimeters away from the center. And they are clearly different. Some aberrations, like for example astigmatism, affect the lens's ability to resolve details in different directions. On this chart, the solid lines refer to the contrast of line patterns along the diagonal, whereas the dashed lines refer to the contrast of line patterns perpendicular to the diagonal. So clearly, the contrast that we get for a certain spatial frequency can vary quite a lot depending on which part of the image we're looking at and depending on how the pattern is aligned with our lens. These MTF charts show us the contrast for sinusoidal patterns, so for the wave patterns that we looked at before. And since any pattern, including the line pattern, can be written as a sum of sinusoidal patterns, we can now look at how our lens affects the contrast of the line pattern. For simplicity, I'm assuming that we've got a perfect lens, so I'm using the line in the MTF chart that refers to the diffraction limit. So for example, we know that the line pattern contains this much of a wave with a frequency of 145 cycles per millimeter. This is the same plot as we saw earlier, but here I'm showing the frequencies only up to the cutoff frequency, roughly. So it looks a bit different. Okay, the lens reduces the contrast of such a wave to 61%. So by multiplying those two values together, we get the intensity of this wave after diffraction. And we can do that for each component of the wave. And if we use the resulting data to reconstruct our line pattern, then we can see that we don't have sharp corners anymore. They've become smoother. And that's because the high frequencies that we need to obtain sharp corners have been muted. The lower frequencies are still there, so the pattern hasn't completely disappeared. If you look at the width of the lines, then you'll see that they are quite narrow. So here we are using a frequency of about 145 line pairs per millimeter. And our contrast is about 77%. This is higher than the 61% contrast that we got for a wave with a frequency of 145 line pairs per millimeter. And that illustrates that the contrast given in the MTF chart is about waves of a certain frequency, not about the frequency of other patterns like the line pattern. So the good news is that if we take pictures of features of a certain frequency, and if those features have sharp corners, then the resulting contrast will be higher than what's shown in the MTF chart. But on the other hand, we can't use line patterns to create an MTF chart, because that would give overly optimistic results. But generally, we don't do that ourselves anyway. Here's another example where we use a line pattern with a lower frequency. The sharp corners have disappeared, but the contrast is still quite high. Keep in mind that what I've just shown you now assumes a perfect lens with where only diffraction affects our image. In a real lens, the effect will be more extreme. Okay, we've seen the impact that a lens has on image resolution and contrast. Now let's have a look at our sensor, because the sensor also affects resolution and contrast. Let's assume that we've got a sensor whose side length is 3.45 micrometers. We saw before that diffraction blurs any pattern with sharp edges, so the light that our sensor receives will never represent a pattern with sharp edges. So we'll look at wave patterns again. For example, this is a wave with a frequency of 36 cycles per millimeter, and the vertical lines represent the boundaries of the pixels on our sensor. If light of that wave pattern hits our sensor, then the pixels will report the average, or sum, of all the light that reaches them. And if we compute our contrast, then you can see that this averaging slightly reduced the minimum and maximum intensity of the light. So our contrast has become a little smaller. If the frequency of the wave increases, then this averaging has a larger effect and our contrast goes down, as you can see in this visualization. Once the frequency of the wave is such that one cycle covers exactly 2 pixels, there's a risk of losing all contrast. It depends a bit on how the wave pattern is aligned with the pixels. For example, here they are not aligned well, so we can't resolve the pattern. And here they are aligned well, so we can see a pattern. If the cycle covers exactly 1 pixel, then we will never get any contrast. As the frequency of the waves increases further, we do see a pattern again. But it's wrong. This averaging of pixels results in an incorrect pattern, and this effect is called aliasing. So the finite size of our pixels clearly has an impact on the contrast of our image. And just like before, we can visualize the effect on contrast in an MTF chart. For lower frequencies, the contrast is still high, and as the frequencies increase, contrast goes down towards 0. The frequency at which contrast is 0 can be calculated as 1 over the width of the pixel. So if our sensor uses smaller pixels, then we can resolve finer details, assuming that the smaller pixels don't suffer from more noise. Due to aliasing, the MTF doesn't stay 0, but it becomes large again, although there we do get wrong patterns. Okay, this curve shown here is for an ideal sensor, where the photosensitive area covers the entire area of the pixel. Real sensors behave a little differently. For example, the photosensitive area will not fill the entire pixel. There may be microlenses on top of the pixels, and there may be electronics to read out the signal, and so on. So the MTF chart of a real sensor will be a little different to this one. Unfortunately, the MTF charts of real sensors are usually not available. Okay, we've seen the impact of diffraction, of our lens, and of our sensor on image resolution and contrast. We've treated them separately, but if you want to know the overall impact of the optical system on resolution and contrast, then you have to multiply the individual MTF charts together. For example, this chart here shows the overall MTF chart of the example that we've been using in this video. Before we finish, I just want to point out that the frequencies and distances that I've talked about in this video refer to the sizes on the sensor. So when I talk about a spatial frequency of 100 line pairs per millimeter, that means 100 line pairs per millimeter on the sensor. If you want to know the corresponding size on the actual objects that you're photographing, then you need to take into account the magnification of your system. But I won't go into details in this video. Good, that's all I've wanted to say about image resolution and contrast. I hope this has been useful. If you've made it this far, then please give the video a like, write a comment and consider subscribing. So thanks for watching and see you soon.